Okay, let's look at another problem. So this is example 3.3, where there is a truck that is traveling at v0 equal to 100 kilometers per hour. So let's start by writing what is given to us. Given v0 equal to 100 kilometers per hour. When the driver slams on the brakes and comes to a stop as quickly as possible, so the intention is that the driver wants to stop the truck for whatever reason. If the coefficient of static friction between the crate A and the bed of the truck is 0.35, so here is a crate and here is the bed of the truck, and between them the coefficient of static friction is given to be as mu s equal to 0.35. So the question is, determine the minimum stopping distance d min and the minimum stopping time t min. So find d min and t min of the truck such that the crate does not slide forward on the truck. So which means that you don't want the crate to move related to the bed of the truck. In other words, the bed of the truck and the crate should move together as a single particle, right? There should be no relative motion between the two. Okay, so let's try to understand this. So if let's say I'm the one who's driving the truck and I want to stop this truck, I can stop this truck very, very slowly, right? I could instead of slamming the brakes, I could apply the brakes softly and then bring the truck to a stop and take my own sweet time in stopping it, right? But the question is saying that you want to stop the truck as quickly as possible, as soon as possible, in the shortest amount of time, in the shortest amount of distance, without letting the crate slip on the bed of the truck. Okay? So now you can imagine, because this is asking for minimum time, minimum distance, you have to basically look at the limiting conditions. So the limiting conditions would be that the crate is just about to slip, right? That will bring it into the impending slip condition. So when it is an impending slip condition, we know something about what the friction forces on the crate would be. And that's an information that we would have to essentially use. Okay. But before we begin to solve the problem, let's look at our method, because I want you to learn how to apply the same method for solving every single problem in this chapter and in other chapters. Okay. We don't have to take an ad hoc or a special approach to solve any problem. So first thing is coordinate system. Clearly it's a linear motion along one direction. So we'll say, okay, we are going to use, a Cartesian coordinate system, and x is that direction. All right. So there's not that much we can do about it. We could fix our reference frame on the ground and indicate the position of this crate, and we'll call that position variable to be x. Okay. So this is not attached to the truck. This is actually attached to the ground. It's not moving, and we are saying this is the position of this. So what is the velocity? Velocity is x dot, and acceleration is x double dot. So if I write in terms of vectors, it will be basically this quantity, right? And this can be also written as dv over dt, or can be written as let me also write I hat, because we're writing everything in terms of vectors, or we can also write this as v dv over dx, which you've seen before that we obtained using a chain rule, right? Okay. Next is free body diagram, right? And free body diagram is very important, because everything that you do after the free body diagram, when you write Newton's second law, the forces that you write on the left-hand side of the Newton's second law have to follow from the free body diagram. It cannot come from anywhere else, okay? So there has to be consistency between your free body diagram, the forces you show on the free body diagram, and what you write in the Newton's second law. So we're drawing the free body diagram of the crate, and that's our particle A, normal reaction. And then it's an impending slip condition, so we know the friction force is mu times n, and then you have gravity, right? And that's your x direction, that's your y direction. So we also show our reference frame. Okay, all right, so now apply the Newton's second law. Which says sigma f equal to ma. So we have mu s n along I direction minus I direction plus n minus mg ax I hat, no y direction acceleration, and that's basically m times v dv over dx, right? The reason we are writing in terms of dv over dx is because if you want to get the x related to velocity, then that's what we will do, and if you're looking for time, then I will do dv over dt I hat. All right, so now let's compare the terms on the left and right hand side. This is minus mu s n, so that's minus mu s n equal to m dv over dt, and we have n minus ng equal to 0. That gives you n directly as mg, which we will substitute in this equation to get minus mu s mg equal to m dv over dt, and cancels. So dv over dt is equal to minus mu s times g. So that's your acceleration along x direction. Okay. So if you look at this, the question is this a constant acceleration? And the answer is yes. So a in this case is constant because mu s does not change and gravitational acceleration doesn't change, right? So if acceleration is constant, then you can safely apply one of the Galileo's equation to solve for the distance traveled or the time, right? Or you could directly use your basic formula, which will allow you to integrate it, right? So we have dv over dt, and I'm going to integrate it, equal to minus mu s g. I will take dt on the other side, integrate this from initial velocity to 0 because it's going to come to stop, 0 to 2t minimum, and that would be minus mu s g times t minimum. The left hand side is minus v0 minus mu s g times t minimum. So that gives you t minimum right away, which is v0 over mu s times g, right? That's part of the answer. Then we are also looking for distance traveled. So I can again go back to my formula for acceleration and write this as dv over dx times dx over dt, which is v dv over dx, and that is equal to minus mu s g, and I'll integrate it, integral v dv equal to minus mu s g times integral dx, changing from 0 to d min, this changing from v0 to v0 to 0, so that's minus v0 squared over 2 equal to minus mu s g times d min. So we get d min equal to v0 squared over 2 mu s g. That's your second answer. Okay, now let's look at another problem where we will employ a curvilinear, in this case tangent normal coordinate system. So in this question, there is a race car that moves at a constant speed v along a bank turn. So let's start by writing what is given to us. So given, we have a car moving at constant speed v, so v is constant, and that means that you can write clearly v dot is 0, right? So the speed is constant, that means that the rate of change of speed, which is v dot, is 0. Let the bank angle and turn radius of curvature be those of Talladega Superspeedway in East Aurora, Alabama, which means that rho is 1100 feet and the turn bank angle is 33 degrees. So radius of curvature is 1100 feet and theta, which is the turn bank angle, as 33 degrees. For this turn, determine the maximum value of v such that the car does not slide. So find v max such that the car does not slide or slip. Assume that the static friction coefficient between the car and the truck is mu s 0.9. So mu s is 0.9. Okay. So these are the things that are given to us. And if you look at the problem, it seems as if you could probably use tangent normal coordinate system because you have speed, you have change of speed given to you as 0, you have radius of curvature, and you can probably try to relate some of those quantities to find the maximum speed, right? So let's start by drawing, what it looks like really. So this is a banked turn, so which means that there is an incline 33 degree, and then you have your car, right? And we will model it as a particle. So that's your car, okay? And we can imagine that the car is really, going into the plane of this diagram, right? Perpendicular to that, because we're looking at a profile picture over here, okay? So how do we solve this problem? Well, let's apply our method, choose the coordinate system. We'll pick tangent normal coordinate system. So let's start by writing that. So we'll use tangent normal system. And in a minute, I'll show you, what tangent direction is, what normal direction is, and so on. And then After that, we'll show our position variables. In this case, there's not much to show in terms of position variables because in tangent normal system, we really don't show the position variable. We talk about velocity and rate of change of velocity. And then we'll draw the free body diagram, right? So free body diagram, let's start with that. So free body diagram. And I'm just going to do it over here. You know what? Let me just do it separately. I'll draw a little bit bigger. So that's theta, and that's my particle, right? That's my car. So what is the tangent direction? Now, tangent direction is really the direction perpendicular to the plane of this figure, right? That's the tangent direction. So I'm not really going to show it to you except to indicate that this is my ET hat. So whenever you want to show a direction perpendicular to a plane, this is the convention. If you just draw a circle with a dot inside, that means perpendicular out of the plane, okay, pointing towards you. So it's coming towards you. If you draw a circle with a cross, that means perpendicular into the plane, because perpendicular to the plane could be either outward or inward. So when you put a dot, that means really coming towards you, and when you put a cross, that means really going into the plane, away from you. Okay, so this is the direction of tangent, so ET hat, which I can't really draw over here, okay, because this is a 2D medium on which I'm drawing. Now, what is the normal direction? The normal direction is basically the direction towards the center, right? And this is the center. This is the center. So EN hat is really pointing this way. This is the direction of EN hat. And ET hat is pointing out from this point, okay? Now, we can take a cross product between ET hat and EN hat and get a third vector, right? So ET hat cross EN hat can give you a third vector. We'll call it EB sub hat. Actually, in differential geometry, this vector is called a binormal vector, okay? So for a spatial curve, you have all these three vectors existing for you. For a planar curve, the binormal vector is always pointing in the same direction. So we also have EB hat. Now, which way is EB hat pointing? Well, depending on which way ET hat is pointing, let's say EB hat is this way. Okay, we know that it's going to be perpendicular to EN hat and EB hat, right? So in this case, it turns out that ET hat should really be going inward, right? So this is how ET hat should be. It should be actually a cross, not coming out of the plane, but going into the plane. That's the only way EB hat would be pointing up, right? Okay, so these are the unit vectors. Now let's draw the forces. So we have normal reaction, we have the weight, okay, and since this is a case of impending slip, right, so this is going to slip. Now you know which way it is going to point. If let's say the car's speed was too much, it'll be basically riding up the incline, it'll be going up, which means that the friction force really should be pointing towards down the incline, right? And these are all the forces that are acting on the car, right? Now we can use Newton's second law, say sigma F equal to ma. So let's resolve all these forces. So let's see, this angle is theta, so this angle is theta too, right? So n has a component along EB hat, so let's write that, n cosine theta and minus mg. So n cosine theta goes in the EB hat direction, mg comes down, and we also have mu s n. So mu s n has a component towards EB hat, that's minus mu s n sine theta, and this is all EB hat, plus we have mu s n cosine theta. We have a component of n also, right? So that's plus n sine theta plus the forces along tangent direction times ET sub hat, right? So that takes care of all the forces in all the directions, and that would be equal to right side, which is m times acceleration, or m times acceleration along EB. Let me write it AB, EB hat direction plus acceleration along normal direction plus along tangent direction. Okay, and we can also write this as MAB EB hat plus V square over rho EN hat, because we know that's the acceleration, and V dot ET hat. Now let's try to simplify the right hand side a little bit. We know that the V dot is 0, so this is actually 0, and we also know that the car actually doesn't move along the binormal direction, EB hat direction, so that means AB is 0. Okay, so that simplifies things a lot. By comparing this with this, we get Ft equal to 0. That's equation 1. Then I will compare the coefficient of EB hat with the coefficient of EB hat over here and get actually n from that. So n cosine theta minus mu s sine theta is equal to mg. So n is equal to m times g over cosine theta minus mu s times sine theta. Okay, so we get the normal reaction from the other thing. And then finally we have the components along normal direction. So let's write that. So we have n times, we write that n times mu s cosine theta plus sine theta, and this is coming from this part, and that is equal to m times v square over rho. So this is equal to m times v square over rho. Okay, so n is known to us, so let's substitute that. So we get mg over cosine theta minus mu s times sine theta times mu s times cosine theta plus sine theta equal to mv. And remember, this is the maximum speed, so I can always add v max square over rho here, because we did put the limiting condition over here, which is that this is impending slip, right? Mu s times n. Okay, so m cancels. That means there's no dependent on the mass. Okay, so what do we get? We get v max square equal to rho times mu s cosine theta plus sine theta divided by cosine theta minus mu s times sine theta, right? So if I want to get just the v max, I'll have to take a square root, and that will be the maximum speed of the car that it can take before it begin to slip. Okay, we'll do one more problem now, and this is a problem where I will try to use a different coordinate system. I'll try to use polar coordinate system. So this is example 3.9. A small sphere is at rest at the top of a frictionless semi-cylindrical surface. The sphere is given a slight nudge to the right. So slight nudge means that it actually started with 0 speed, so that it slides along the surface. Determine the angle theta at which the sphere separates from the sphere. Now there are several important things going on here. So number one is that it was given slight nudge, right? So given is that its initial velocity is 0. And then second is that so that it slides along the surface. Now imagine if you really have a sphere of appreciable size and you roll it along a semi-cylindrical surface like of the sort that is shown in this figure, you know that it's going to actually roll, right? It's not going to slide, it's not going to skid. It will, in all likelihood, it is going to roll, just like your bowling ball rolls. It could slip too, though. So the point of mentioning this, that it slides, is that you are not going to regard this sphere as a rigid body object. You're going to treat it as a particle, because only the particles can slide, right? Particles cannot really roll because they don't have any shape, right? So that's the reason why it is emphasizing this, that it slides along the surface. So implicitly it is telling you how you should really model the sphere in this case, which is a particle. So the question is, determine the angle theta at which the sphere separates from the surface. Okay, so we know that when it separates from the surface at the theta 0, let's say this is when, or let me call it theta f. Okay, at theta f, when it separates, we know the normal reaction would be 0, right? So there will be no reaction on the sphere from the semi-cylindrical surface when it leaves the surface. Okay, so these are the things that are given to us. So how do we solve this problem? First thing is we need to pick a coordinate system. So we'll pick let's say r theta coordinate system, right? So let's say here is the sphere somewhere in between, and I'm going to show the radial direction, that's er hat, and I'll show a theta direction. Since this is the increasing theta direction, I will pick my e theta hat vector to point that way, right? We know that e theta hat should always point in the direction of increasing theta. Okay, the next step is to do the kinematic analysis. And that in this case would be simply writing velocity and acceleration. So r dot er hat plus r theta dot e theta hat, right? We can simplify this because we know that this distance will always be capital R, right? That r is not changing. That means r dot is 0. So we'll have r times theta dot e theta hat as the velocity, and acceleration is r double dot we can simplify this as well. R double dot would be 0. r dot is already 0. So what is the acceleration? Acceleration is minus r, which is fixed, theta dot squared er hat plus there's no 2, sorry, there's no 2, so we only have r theta double dot, so r theta double dot e theta hat. Okay, so that's the acceleration, right? We don't know what theta dot is, we don't know what theta double dot is, we cannot assume any of it to be 0, so we will leave it at that, right? So we'll call this equation 1, we'll call this equation 2. Okay, all right, so if this was a kinematics problem, you would probably end it over here, right? Unless there was something more given to you. Okay, all right, so next step is to draw free body diagram. So free body diagram, we have the particle, right? And I'm just going to draw this semicircular thing just to indicate where this position might be. So we have, this is the center, we have the normal reaction, we have mg, there's no friction, so those are the only forces acting on this particle. Now remember, I'm drawing the position of this sphere modeled as a particle somewhere between when it starts its journey from the top of the surface and when it's going to leave the surface, right? Because I don't want to draw this free body diagram at a special situation and at a special position, because if I draw it at the time when it's leaving, then I have to show the normal reaction to be 0. But I don't want to do it because I want to account for normal reaction and then make it 0 at a certain theta, right? Okay, and this angle is theta, right? All right, so let's resolve this along our er hat in theta e theta hat direction. So I need to show my er hat e theta hat, right? Okay, second law, sigma f equal to mass times acceleration. What are the forces? So we have this angle is theta, so this angle is theta, right? There's no, n is completely along the direction, so that's n. Okay, we'll write that. Mg has a component, right, along the direction. This angle is theta, so that would be minus mg cosine theta er hat. And then we have mg sine theta, which is along e theta hat direction, equal to mass times acceleration, right? Now we can use the acceleration from equation 2 and substitute here, right, in 3. So let's do that. So I'm going to come down here actually for the space reason, and minus mg cosine theta er hat plus mg sine theta e theta hat is equal to m times, and my acceleration is minus r theta dot square er hat plus r theta double dot e theta hat. Okay. All right, so we have this vector equation. We can get two scalar equations out of it by comparing the coefficients of unit vectors, right? So let's compare the coefficients of radial direction unit vector, and we get n minus mg cosine theta equal to m times r theta dot square and minus sign in the front. And we also get mg sine theta equal to m r theta double dot, right? So we'll call this equation, I don't know, 4 and 5, okay? All right, so now remember, our objective is to determine the angle theta at which the sphere separates from the surface, right? So when it separates from the surface, the normal reaction would have to be set to 0, right? But even if we set n to be 0 in equation 4, we don't know what theta dot is. So first thing we have to determine is what the theta dot is. Okay, so how can we determine theta dot? Now, theta double dot is completely known to us, right? Because this m cancels and we get theta double dot to be equal to g sine theta over r, right? So does this look kind of familiar to you compared to what we have done before? Actually, it does. So you will recall that in the past, we looked at the acceleration, right? Let's just call it acceleration, not ax, given as a function of x. And if this was given to you as a function of x, you could actually compute the velocity, right? Because you could write acceleration as v dv over dx, and this was a function of x, and you could bring these two things together, and then you could integrate it. It's a similar situation over here too. We have theta double dot, which is like angular acceleration, so it's the rate of change of angular velocity or rate of change of theta dot, and then we have theta here, right? So we can do the change of variable here. So we'll write this as d over dt of theta dot, right? Because that's theta double dot. and that is nothing but d over d theta of theta dot times d theta over dt. So change of variable. So the role that v is playing here is being played by theta dot here, right? And the role that x was playing here is being played by theta here. Okay? So what is d theta over dt? What is this quantity? That's nothing but theta dot. So we can write this as theta dot times d over d theta of theta dot. Now compare this with what you have here. It's almost identical, right? It's similar. So we have v and you have theta dot here, and you have x, you have theta over here, right? So a linear variable is being just replaced by an angular variable. Okay. So now let's substitute this in here. What do we get? Theta dot times d theta dot over d theta equal to g sine theta over r. This is easy to integrate because I can take d theta on this side. I have theta dot d theta dot equal to g sine theta over r times d theta. We'll integrate this. Theta is changing from 0 to some theta that we need to find. We'll call it theta f. Theta dot is changing from 0. Why? Because initially it was at rest, right? Okay. And we're looking for the theta dot, right? At theta f. So what is this? This is theta dot squared over 2 equal to g over r. And what's the integral of sine theta? It is minus cosine theta. So that's cosine theta changing from 0 to theta f equal to minus g over r, and that's cosine theta f minus cosine 0, which is 1. So this becomes g over r, 1 minus cosine theta f, and that's theta dot squared over 2. So I can take 2 on this side and write this as 1 minus cosine theta f. In fact, I could compute theta dot at any given value of the theta, right? Because this is a general expression which I'm integrating. So I don't have to necessarily put theta f here, not yet, okay? So I could get a general expression for theta dot from this. All I have to do is just replace theta f with this theta, and that will be a general expression for theta dot. Okay, so now we have the theta dot. We can substitute that in equation number 4 over here, right? Because this is where we have theta dot squared. So let's do that. So we'll substitute theta dot squared. So, but let me first write equation 4 once again, because this is a little bit far off. So equation 4 again. So equation 4 again is n minus mg cosine theta equal to m times r theta dot squared to minus sine r theta dot squared. So this is minus m r times. Now let's substitute theta dot squared from here. 2g over r 1 minus cosine theta. Okay. And on the left hand side, we have n. What is the value of n? Well, we don't know that. That's what we're trying to find, right? So n minus mg cosine theta. So when the sphere leaves the surface, n goes to 0. Okay, this becomes plus. M cancels, g cancels. So what do we get? We get actually r cancels too. So cosine theta equal to 1 minus cosine theta. And we have a 2 here. So what do we get? We get 3 cosine theta equal to 2, which gives you cosine theta equal to 2 over 3. So theta is cosine inverse 2 over 3. And that's the angle at which the sphere is going to leave the surface.